Imagine a region of space so dense that nothing can escape it. Not matter, not light, not even information. Gravity is so strong that space-time itself curves into an inescapable pit. This is a black hole, and it's the ultimate laboratory for testing the limits of physics. Black holes shouldn't exist. General relativity predicts them, but Einstein himself didn't believe they were real. He thought nature would find a way to avoid such extreme conditions. He was wrong. Black holes exist. We've detected them indirectly for decades and photographed one directly in 2019. But their existence creates paradoxes that threaten to break physics. At the center of every black hole is a singularity, a point of infinite density where space and time cease to exist. General relativity predicts this, then breaks down, unable to describe what happens there. Quantum mechanics suggests information cannot be destroyed, but black holes appear to destroy it, swallowing matter and erasing its quantum state forever. This is the information paradox, and it's been driving physicists mad for 50 years. Stephen Hawking showed that black holes aren't completely black. They emit radiation and eventually evaporate. But this radiation seems to contain no information about what fell in. Information is lost. This violates quantum mechanics. Physicists proposed wild solutions: information encoded on the event horizon, holographic principles, firewalls that incinerate anything crossing the boundary. Each solution creates new problems. Black holes also warp time. Near the event horizon, time slows to a crawl. If you fell into a black hole, from your perspective, you'd cross in finite time. But to an outside observer, you'd appear frozen at the horizon forever, never quite falling in. Who's right? Both. And neither. Welcome to black holes, where Einstein meets quantum mechanics and both theories scream in agony. Where reality becomes so extreme that our best physics collapses. And where the ultimate secrets of the universe might be hidden, waiting for a theory that doesn't exist yet. Black holes emerged from Einstein's general theory of relativity in 1915. Relativity describes gravity not as a force, but as the curvature of spacetime. Massive objects warp space and time around them, and this curvature is what we experience as gravity. Just months after Einstein published his equations, physicist Karl Schwarzschild found an exact solution. Schwarzschild calculated the spacetime geometry around a perfectly spherical, non-rotating mass. He discovered something shocking. If you compress enough mass into a small enough radius, spacetime curves so severely that nothing can escape, not even light. This critical radius is now called the Schwarzschild radius, or the event horizon. For the Sun, the Schwarzschild radius is about 3 kilometers. To become a black hole, the entire Sun would need to be compressed into a sphere smaller than a small city. For Earth, it's about 9 millimeters, the size of a marble. These seemed absurdly unrealistic. Einstein himself rejected black holes, arguing that nature wouldn't allow such extreme compression. But in the 1930s, astrophysicists realized that massive stars could create black holes. When a star exhausts its nuclear fuel, it can no longer support itself against gravity. If the star is massive enough, more than about 20 times the Sun's mass, no known force can stop gravitational collapse. The star implodes, compressing into an infinitesimally small point, a singularity. Around this singularity forms the event horizon. Anything crossing the horizon is doomed. It will inevitably reach the singularity and be crushed to infinite density. The term black hole was coined by physicist John Wheeler in 1967. Before that, they were called frozen stars or dark stars. Wheeler's name stuck because it captured the essence. These objects are holes in spacetime, and they're perfectly black, emitting no light. For decades, black holes were theoretical curiosities, but astronomers found indirect evidence. In the 1970s, they discovered Cygnus X-1, an intense X-ray source. The X-rays came from gas spiraling into an invisible object with several times the Sun's mass. The only explanation: a black hole. Since then, thousands of black hole candidates have been identified. Some are stellar mass, formed from collapsed stars. Others are supermassive, millions or billions of times the Sun's mass, lurking at the centers of galaxies, including our own Milky Way. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's event horizon. The image showed a glowing ring of gas around a dark shadow, the silhouette of the black hole at the center of galaxy M87. This black hole has 6.5 billion times the Sun's mass. The image confirmed general relativity's predictions with stunning precision. But understanding what happens inside remains a mystery. The event horizon is a boundary in space-time. It's not a physical surface. You could cross it without feeling anything special. But once you cross, escape is impossible. The future direction of space-time itself points inward, toward the singularity. All paths lead there. Trying to escape is like trying to travel backward in time. Impossible. What's inside? General relativity predicts a singularity, a point where density and space-time curvature become infinite. At the singularity, the equations of general relativity break down. They produce infinities, which signal that the theory is no longer valid. Physicists believe a quantum theory of gravity is needed to describe singularities, but we don't have such a theory yet. So what happens at the singularity is unknown. Some speculate it's a gateway to another universe. Others think space-time ends there. Still, others believe quantum effects prevent true singularities, replacing them with ultra-dense but finite cores. Black holes also create time dilation effects. The closer you are to the event horizon, the slower time passes relative to distant observers. If you watch a clock fall toward a black hole, it appears to slow down, ticking more and more slowly as it approaches the horizon. The clock never quite reaches the horizon from your perspective. It appears frozen in time, red shifted into invisibility. But from the clock's perspective, it crosses the horizon in finite proper time. This creates a paradox. From outside, the black hole takes infinite time to form. Collapsing matter never quite reaches the horizon. But from the perspective of infalling matter, the black hole forms quickly, and you cross the horizon in moments. Both perspectives are correct in their own reference frames. This relativity of simultaneity is central to understanding black holes. Then came Stephen Hawking's bombshell. In 1974, Hawking combined quantum mechanics with general relativity and discovered that black holes aren't completely black. They emit thermal radiation, now called Hawking radiation. This radiation arises from quantum fluctuations near the event horizon. Virtual particle-antiparticle pairs pop into existence near the horizon. Normally, they annihilate immediately. But near a black hole, one particle can fall in while the other escapes. To an outside observer, the black hole emits particles. This radiation has a temperature inversely proportional to the black hole's mass. Stellar mass black holes are incredibly cold, much colder than the cosmic microwave background. But tiny black holes would be hot, eventually evaporating completely. Hawking radiation has profound implications. It means black holes aren't eternal. They slowly lose mass, radiating energy into space. A black hole with the Sun's mass would take 10 to the 67 years to evaporate, vastly longer than the current age of the universe. But smaller, black holes evaporate faster. A black hole the mass of a mountain would evaporate in seconds, releasing tremendous energy. Hawking radiation also created the information paradox. In quantum mechanics, information is never destroyed. The state of a system evolves deterministically according to the Schrödinger equation. If you know the initial state perfectly, you can in principle predict all future states and retrodict all past states. Information is conserved. But black holes seem to violate this. Matter falls in, carrying quantum information, its position, momentum, spin, charge, and countless other properties. That information crosses the event horizon and reaches the singularity. Later, the black hole evaporates via Hawking radiation. But Hawking radiation is thermal, random, with no information about what fell in. It's like burning a book and claiming the smoke contains the text. The information is gone, destroyed. This is the information paradox. Hawking initially embraced this conclusion. He argued that black holes destroy information, and quantum mechanics must be modified in the presence of strong gravity. But most physicists found this unacceptable. Destroying information violates unitarity, a fundamental principle of quantum mechanics. If information can be destroyed, then quantum mechanics isn't universally valid. This would have profound consequences for everything from particle physics to quantum computing. So physicists searched for ways to save information. One idea: information is encoded on the event horizon. When matter falls in, its information isn't destroyed, but imprinted on the horizon's surface. Then, as the black hole evaporates, this information is gradually released in subtle correlations in Hawking radiation. This leads to the holographic principle. The holographic principle, developed by Gerard 't Hooft and Leonard Susskind, states that all the information contained in a volume of space can be encoded on the boundary of that region. For a black hole, the information about everything inside is encoded on the event horizon. The event horizon has a finite area, and the maximum information it can store is proportional to that area measured in Planck units. This is the Bekenstein bound. The holographic principle suggests that our three-dimensional reality might be a projection from information encoded on a two-dimensional boundary. This idea inspired ADS-CFT correspondence, a mathematical relationship between gravity in three-dimensional space and quantum field theory on the two-dimensional boundary. It's one of the deepest insights in theoretical physics, hinting at a profound connection between quantum mechanics and gravity. But the holographic principle raises new questions. How is information encoded? How is it transferred from the interior to the horizon? And how is it released in Hawking radiation without creating paradoxes? In 2012, physicists discovered a new problem: the firewall paradox. If information must escape in Hawking radiation to preserve unitarity, then the radiation must be entangled with particles inside the black hole. But if an infalling observer crosses the horizon smoothly, as general relativity predicts, then the horizon must be empty space. No drama, no firewall. You can't have both. Either the horizon has a firewall, a wall of high-energy particles that incinerate anything crossing, or information is lost. This is the firewall paradox. The firewall seemed to destroy the equivalence principle, Einstein's insight that free fall is indistinguishable from being in empty space. At the horizon, you shouldn't feel anything special, but a firewall would vaporize you. This crisis forced physicists to reconsider fundamental assumptions. One proposal: ER equals EPR, developed by Juan Maldacena and Leonard Susskind. ER stands for Einstein-Rosen bridges, wormholes connecting distant regions of spacetime. EPR stands for Einstein-Podolsky-Rosen, quantum, entanglement. Maldacena and Susskind proposed that entanglement creates wormholes. Every pair of entangled particles is connected by a tiny wormhole. This suggests spacetime itself emerges from quantum entanglement. If true, it would unify general relativity and quantum mechanics in a profound way. Another idea: black hole complementarity. This principle, proposed by Susskind, states that information is both inside the black hole and encoded on the horizon, but no single observer can see both. An infalling observer sees matter cross the horizon and hit the singularity. An outside observer sees information encoded on the horizon and released in radiation. Both descriptions are correct, but they're complementary. You can't compare them because doing so would require faster-than-light communication. This is similar to Bohr's complementarity in quantum mechanics, where particles are both waves and particles depending on measurement. Recent developments involve quantum gravity theories. String theory suggests black holes are made of strings and branes, with no singularity, just a dense configuration of quantum objects. Loop quantum gravity proposes spacetime is discrete at the Planck scale, preventing singularities. In this view, black holes have cores with finite density, possibly bouncing into white holes, hypothetical regions where matter explodes outward. These ideas are speculative, but offer glimpses of how quantum gravity might resolve black hole paradoxes. Another mystery: the entropy of black holes. Jacob Bekenstein showed that black holes have entropy proportional to their horizon area, not volume. This is bizarre. For normal objects, entropy scales with volume, but for black holes, entropy scales with surface area. This is a clue that gravity is holographic, and it suggests that black holes are the most entropic objects in the universe. They maximize disorder. Throwing matter into a black hole increases the universe's total entropy. This ties to the second law of thermodynamics: entropy always increases. Black holes are entropy engines. Black holes also exhibit remarkable simplicity. The no-hair theorem states that black holes are characterized by only three properties: mass, electric charge, and angular momentum. Everything else, the hair, is lost. Two black holes with the same mass, charge, and spin are indistinguishable, regardless of what formed them. This is surprising. It means black holes have minimal information, yet maximal entropy. This tension drives much of the information paradox. Rotating black holes, Kerr black holes, are even stranger. They have two horizons, an outer event horizon and an inner Cauchy horizon. Between them is the ergosphere, a region where spacetime is dragged around the black hole. Inside the Cauchy horizon, the singularity isn't a point, but a ring, and there might be regions where you could enter the black hole and emerge elsewhere, perhaps in another universe. But these pathways are unstable. Quantum effects or slight perturbations destroy them. It's unclear if they're physically real or just mathematical artifacts. Supermassive black holes, millions to billions of solar masses, reside at galactic centers. They grow by accreting gas and merging with other black holes. When black holes merge, they release gravitational waves, ripples in spacetime. In 2015, LIGO detected gravitational waves from merging black holes for the first time, confirming a major prediction of general relativity. These detections allow us to study black holes directly, measuring their masses and spins. And they're the loudest events in the universe since the Big Bang, releasing more energy in seconds than all the stars in the observable universe combined. Black holes are also connected to the holographic principle and quantum entanglement in ways we're just beginning to understand. The interior of a black hole might be a highly entangled quantum state, with information distributed non-locally. This connects to ideas about quantum error correction and tensor networks, mathematical structures describing entanglement. Some physicists believe spacetime is woven from entanglement, with black holes as extreme examples of this fabric. So, where does this leave us? Black holes reveal the boundaries of our best theories. General relativity and quantum mechanics both work brilliantly in their domains, but at black hole singularities and horizons, they clash. Information paradoxes, firewalls, complementarity. These are symptoms of a deeper problem. We need quantum gravity. Candidates include string theory, loop quantum gravity, and others. But none are complete or experimentally confirmed. Black holes might hold the key. By studying them, through gravitational waves, X-ray emissions, and theoretical models, we probe the limits of physics, and we inch toward a unified theory. Perhaps one day, we'll understand singularities. We'll know whether information is truly lost or subtly preserved. We'll resolve the firewall and complementarity. We'll see how spacetime emerges from quantum entanglement. We'll grasp the holographic nature of reality. Or perhaps black holes will remain forever mysterious, their interiors hidden behind horizons, their singularities beyond the reach of any theory. Either way, black holes are the ultimate frontier, where physics breaks down, where mysteries abound, and where the deepest truths about the universe might be waiting, just beyond the edge of what we can understand.